Hey everybody. We're starting 4.3. It's actually the last section in our textbook. And if you recall, back in ancient times, we used derivatives to figure out, maximums and minimums, of two-dimensional curves. Well, guess what? We could use that to get maximums and minimums, maximums and minimums um, on three-dimensional surfaces, and that's what we're going to do right now. So we're going to call that. Well, you know what? We're going to call it optimization, and we're going to use derivatives, and it's going to be awesome. So let's get started right now. With no further ado, here we go. The first thing I need to do is to lay some formulas on you. Sorry about that, but we got to do it. And then I'll explain what the formulas mean and how to use them. So we want to I'm making a list of just like we had first derivatives and second derivatives when we were dealing with just one variable. Um, so to here we're going to have first derivatives and second derivatives. We showed you in the previous section how to do first derivatives, and now second derivatives. Well, that's a funny thing, you see, because there are two variables. There's x and y. So there's actually like four combinations. I could do x first and then do x second. That's a second derivative. I could do y first and then y second. That's a second derivative. But as you see from this beautiful table I'm giving you, as right in front, I could make my first derivative with respect to x and my second derivative with respect to y, or vice versa. So there's a lot of there are pretty much four variations of what to do. Now, again, it's not that complicated. I'm just going to do taking a first derivative and a second derivative. Other than that, it's similar to what we did, with one dimension. You take a derivative, then you take the derivative of the derivative. Now, so we did it before with a function of one variable. That was with our two-dimensional, calculus. And now we're doing it with a function of two variables in our three-dimensional calculus. Uh, so so what do you so when I say take the derivative uh with respect to x and then take it with respect to y, so like I said before, when I take the first derivative, I'm going to treat x like the constant. I'm sorry, x like the variable, y like the constant. That's when I take the derivative with respect to x, and then when I take the derivative with respect to y, I'm going to treat y as the variable. I'll treat x as the constant. It's kind of nothing. Even though this looks all new and big formulas and everything, it's nothing really different than we haven't seen already. It's really nothing very different. The mechanics of it, I should say, are nothing different than what we've seen already. Okay, let me give you some. Let me just lay some more understanding on you. Okay, well, the first thing we're gonna have to do is switch cameras. So let me switch cameras, and now I have to. Oh, I disappeared. That's my hand. I got to get rid of this background. I like this background. By the way, full disclosure, I'm not actually. I was never actually in outer space. It was just a background, so I have to get rid of it now. I'm sorry, and I'm sorry if I deceived any of you. If any of you actually thought I was in outer space or any of these other places that we've been looking at. Actually, I like writing this way. Okay. Anyway, this is section 4.3, but in retrospect, I would be happier holding the paper this way. Okay. So I'm going to give you a function, and we're going to take second derivatives. But like I say, there are four possibilities. So let's start with a nice little function. Let's start with f of x comma y. So as an example, f of x comma y. So it's a function of two variables. And by the way, remember I used to always say that y equals f of x, is y and f of x are synonymous. So this is really z. Z equals f of x comma y. But anyway, uh, f of x comma y equals x squared minus 4xy plus 4y squared. That's x squared minus 4xy plus 4y squared. And let's take the partials now, the first derivatives. We're going to take the first partials. So I'm going to take fx, and I'm going to take fy. Now, of course, I could just write fx and fy and you get the point, or I could write it this way, fx of x comma y, write it that way. Just like I used to write y prime, or sometimes I write y prime of x, So anyway, let's do it. All right, so for fx, meaning the derivative of this guy up here, treating x as a variable and y as a constant, well, this is a variable, so that's 2x. The derivative of x squared is 2x. Here, this is x is a first degree, polynomial, if you will, and therefore the derivative is just -4, but not just -4, -4y, because the y is considered like a constant. Like if it was -4b x, the derivative will be -4b. Now it's -4y, same thing. And this is completely a constant. So therefore, the derivative here is just 0. Pretty awesome. Okay, so I'm gonna go. Let me see if I can get in a little closer for you guys. Make the picture a little bigger. It's always a see, the thing is like this. If I go in too close, then you don't see the whole page. If I'm too far, then it's smaller. That looks pretty good. Okay, f of so that's f of x. That's f x. I mean the derivative. So this is the partial derivative of the function f, of the two variable function f. It's a partial derivative with respect to x, and this guy just becomes a total zero. It disappears. Now, for the second one, we're going to look at the same original function f of x comma y, and we're going to take the derivative of this with respect to y, meaning we're treating y as a variable and we're treating x as a constant, which means when I look at that x squared, I don't differ. I just that's just a constant. So the derivative of a constant is 0, so it just disappears. Or as my math teacher used to say, it goes on vacation. Now here, y is a variable and -4x is the constant, so it's just -4x. And here, y is a variable, so this just becomes plus 8y. That's my story, and I'm sticking to it. So -4x plus 8y is the derivative, the partial derivative with respect to y. Now I'm going to do a second derivative. So I'm gonna so these are the first derivatives. These are the first partials. These are the first partial derivatives. Okay, now for the second partials. So I'm gonna write fxx, which means the first derivative will be with respect to x, which we did already. Then the second derivative is going to be of this with respect to x. So again, I could just write fxx, and you get the idea. I could write it more fully, fx of x comma y. Depends on how formal I want to be. For now, I'll be a little more formal. I might be a little more informal, at other times. Anyways, so I'm not looking at the original function anymore. I'm looking at the first derivative. So I'm looking at the first derivative with respect to x was 2x minus 4y. Now I'm going to take a second derivative with respect to x. So I have 2x. So I'm looking at this guy right up here, the first example, this right where I'm pointing. I'm looking at that. The derivative of 2x, as we know, is just 2. The minus 4y, well, y is just a constant in this scenario, so the derivative is 0. And that's it, we're done. Now, fyy of x comma y, of these two variables, well, my first derivative is this guy downstairs. And I want to take the derivative, the second derivative is with respect to y. So so the minus 4x, that's just a constant. It goes on vacation when I take the derivative. And here, this is the 8y is my variable, y is the variable, so the answer is just 8. That's my second. Now, are we always lucky enough that it comes out to be just a plain number, not a function? Not necessarily, but in this case, it's a plain number. Now, let's mix and match. So I'm going to look at this one, fxy of x comma y. And that means we're going from which is my left, from left to right. So my first derivative is going to be with respect to x. That means I'm looking at this guy up here, this top guy right there, almost top guy right there. And then my second derivative will be with respect to y. So I'm looking at 2x minus 4y, and I'm taking the second derivative, and that's just negative 4. Now the last case is f of yx of x comma y. So it means first I do my first derivative with respect to y, which is this bottom line right here. And the next derivative I'm going to do is with respect to x. So you have minus 4x. The derivative of that is negative 4. But 8y, that's really just a total constant. So when I take a derivative, it just goes on vacation. So these are the second partial derivatives. Now, some of you who are very sharp may have noticed that when I take these last two examples here, these last two cases, I should say, not examples, last two cases, fxy and fyx, if you notice, some of you may have noticed I got the same answer. I got, well, I can't, I got negative 4 for both of them. Now, is that a coincidence? Or is that a small miracle? Is that a coincidence? Well, actually, it's not a coincidence. It is actually a theorem. It's a theorem that when you take this mixed derivative, meaning first x and then y, you're always going to get the same answer, even when you switch the order. So I want to share my screen with you and show that to you as a theorem. So hold on a second. I'm going to go share. Just going to share the screen. I want to show this to you as an official theorem. And here we go. So let me get this out of the way. So the mixed partial derivative theorem. So if f and fx, which is the first derivative with respect to x, and the first derivative with respect to y, and the second derivative xy and the second derivative yx, if all of these guys are continuous functions, and obviously differentiable because I can take a derivative, then fxy equals fyx, and this will always happen. So as long as f and all of its appropriate partial derivatives are continuous, well, f obviously has to be continuous because you couldn't take a derivative that's not continuous. But there can be no breaks in the graph. The mixed partials are equal, even if they are of higher order, and even if the function has more than two variables. So that's kind of cool. That's kind of cool. And that's going to be very useful as we're about to see right now. And of course, that means I'm going to give you another example. Let me go back to my trusty, oops, where'd it go? Trusty paper. I'll get it. And okay, so let me explain now. Let me give another. Sorry, I can't even talk anymore. I'm so excited that I'm tripping over myself. Anyways, what I want to do is I want to do an fxy and fyx for the following function. So let's switch pens. You know what? This is all. I'm just gonna switch papers. Okay. So I want to look at this function here. F of x comma y. F of x comma y. Actually, let me write an example here. F of x comma y is equal to e to the x plus y over y cubed plus y plus y ln y, ln y. And why not? You get it. See what I did there? So let's take some derivatives here. Let's get all these, let's get fx, fy, and so on and so forth. So fx, that's going to be equal to, let's see, I'm going to use quotient rule here. So I'm going to do the derivative of the top, which is just e to the x plus y. There's no chain rule here because chain rule won't do anything here, I should say. Minus times the bottom, so f prime g times the bottom, y cubed plus y, um, minus the top, e to the x plus y, times the derivative of the bottom, and that's 3y squared plus y. And we'll deal with that more in a second. Or do I want to deal with that now? I'm thinking here. What do I want to do? Let me first, before we do anything, I just want to change this y into a 1. Because we're looking at this, we're looking at the derivative of the bottom. So the derivative of y cubed is 3y squared, and the derivative of y is 1. So it should be a 1, not a y. So sorry about that. And of course, that's all over the bottom squared. Y cubed plus y squared. That's my g squared. Okay. The next thing I need to do is take the derivative of this guy. That's going to be very easy because as far as x is concerned, y is just a constant, so just goes to vacation. Now let's see if we could simplify this thing a little bit. Okay, now the next thing I want to say, I guess is good news and bad news. The good news is that this can be very simplified very fast, and the bad news is my brain just sometimes people's brains temporarily short circuit. I'm sorry about that. Happens to everybody, even people who whatever do math all the time. So um, I failed to remember actually uh, that the y is a constant as far as x is concerned. So really, this whole thing, the derivative of the bottom is the derivative of a constant. So this whole thing is going to go on vacation. And now I have y cubed plus y on top, y cubed plus y squared on the bottom. So finally, fx is just going to be e to the x plus y over y cubed plus y. And that's it. But that's not all. That we're not done yet. That's just for this. That's just for this part right here. I have to do the very difficult part of this guy right there. And guess what? That's zero because it's all a constant. Derivative is zero. Oh, I might have said that before. Sorry. Anyway, done. Now let's do fx. Let's do fy. Fy, well, that is going to equal to now here, y is going to be the variable and x is going to be the constant. So again, I'm going to use quotient rule, and the derivative of the top is still e to the x plus y times the bottom, which is y cubed plus y. Now this happens to be the same as that, but that's just the way it is. Even though here I treated y as a constant, here I treated y as a variable, x is a constant, but okay, it happens. And now, but finishing the quotient rule, I do minus the top, e to the x plus y, times the derivative of the bottom, which is what I put over here. The derivative of the bottom is 3y squared plus 1. And all that is over. Well, before I do write the bottom, I'm going to simplify the top a little bit. We'll be happy to simplify it more, but I'm doing as much as I can. And that's going to be e to the x plus y times y cubed minus 3y squared plus y minus 1. Now, I just like I like putting polynomials in descending order of exponent. That's why I mixed. That's why I switched them around. Anyway, all that is over the bottom squared. And now, even though fx and fy don't look anything like each other, well, let's see what happens when I do fxy. So I'm going to switch color. Fxy is going to be as follows. So in other words, I'm taking the first derivative with respect to x, and then I'm following by taking the derivative of this guy with respect to y, which actually should be by now we should be experts at it. And that's going. Oh, wait a second. Whoa. I'm sorry. I jumped the gun. Boy, I'm really getting jumping guns over here. Okay. I'm thinking I should redo this whole video because I'm making too many mistakes. Yeah, let's do it. Let's that's what happens on live TV. Um, see, we did the see when we did X, this last guy here didn't matter. But now that we're doing Y, this last guy over here does matter, so I have to put that in. I failed to do that. I forgot about it. So this is product rule. So it's F prime G, so it's just ln Y plus FG prime, which is plus Y over Y, which is of course is just one. Okay, that's so that's plus, and I'm not going to combine these fractions or anything. But don't worry about it because when I take fyx, that whole thing's going to disappear. So don't even worry about it. Anyway, a lot's going to disappear, by the way, when I do that. But I don't want to give anything away too fast. So fxy, I'm going to now I'm back up here. I'm taking the derivative here with respect to y. So I'm going to again, well, I'm going to use product rule again. So I have the top f prime g, so that's equal to f prime g, which is e to the x plus y times g, which is y cubed plus y, minus e to the x plus y times g prime, which is 3y squared plus 1, over y cubed plus 1 plus y squared, which is going to be really the same as this guy right there. It's going to be e to the x plus y times, let's see, y cubed minus 3y squared plus y minus 1, and all that is over y cubed plus y squared. Okay, now this is fxy. So let's put that right there. So I just want to make a special note of that. That I'm gonna even use pink. Oh, all right, so much that pink. Next, let's look at fyx. So I'm gonna no fyx. Well, that's not so bad because really for fyx, this entire thing here is just a constant. Okay, so let's look at fyx. So as far as x is concerned, this whole thing is just a constant that's multiplying the e. So the derivative is going to be that same constant times so I'm going to take the derivative of e to the xy, which is just e to the xy, x plus y in this case, because y is just a constant, and 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 all I'm doing is taking now this constant, I just bring it down. Y cubed minus 3y squared plus y minus 1. And here, bring down the rest of the constant, y cubed plus y squared. And the derivative of this part with respect to, now I didn't even bother simplifying because I know it's all going to disappear anyway, so why do all that work? Now I take the derivative here with respect to x, but it all just goes on vacation. So I'm left with this right here. Let me but if you'll notice this right here is exactly the same as this right here. So my fx, so my fxy and my fyx came out to be exactly the same thing. Even though everything was looking so different, as we were going through this, but then when we got to the end, it all wound up being the same thing, which is so awesome and cool and remarkable. Alrighty. Now, oops, there we go. Everything that we did here is just um, everything we did here is just um, showing how to manipulate, the derivatives, the first and second derivatives in two variables. And well, I'm gonna do something also fun. Like this one, blur mode back. I I I know I seem like a kid playing with a new toy. That's only because I'm playing with a new toy and I'm kind of like a kid. But anyway, everything we did in today's video is just how to take these first and second derivatives, how to mix them and match them, and to show that the order won't matter whether I do X then Y or Y then X. By the way, so what should you do? Usually, you might do whichever one is easier. You see what I'm saying? But you're going to get the same answer. I like doing both, because it's like a way of checking my answer. If I do FXY versus FYX, and I get different answers, then I know I must have made a mistake somewhere. So I like doing things both ways as a way of checking my answer. But anyway, uh, that's it for today's video. For this particular video, this is just part one. This is just part one. So I'm going to stop it here. The next video, part two of this section 4.3. Now that we did all this work in mechanics of taking how to take these derivatives, I still didn't tell you what that is used for and how that's going to give us these maximums and minimums and all these other cool things. So that we're going to do in the next video. Anyway, just wanted to say how much fun it was, and bye.